can start. So, good afternoon, everybody, and welcome to this keynote talk by Max Ovsjanikov. Well, Max is a professor at École Polytechnique in France. He works on 3D shape analysis with emphasis on shape matching and correspondence. Max has received a Eurographics Young Researcher Award in 2014 in recognition of his outstanding contributions to theoretical foundations of one-rigid shape matching. He has served on the technical program committees of international conferences, including SIGGRAPH and SIGGRAPH Asia. He is a member of the editorial board of Computer Graphics Forum and has co-chaired the symposium on geometry processing in 2016. In 2017, he received an ERC starting grant from the European Commission and the bronze medal from the French CNRS in 2018. And today, Max will talk about functional approaches for representing and analyzing 2D shapes with and without learning. So Max, all yours.
Okay, thank you very much. Thank you, Marco. And first of all, I want to thank the organizers for inviting me. It's a great honor for me to give this keynote. And I basically want to first emphasize that I'm going to present a lot of the work that was done in collaboration, of course, and especially with some of my students whose names are mentioned here, and also with some of the colleagues. And even as I will describe with some people who might not realize that they have contributed to some of this work. And so basically the motivation for the work that I've been doing and we've been doing with my colleagues for the past 5 to 10 years is that when you're dealing with geometry, there are many different kinds of representations. You can have shapes represented as point clouds, triangle or quad meshes. Sometimes you have volumetric representations, which are common in medical imaging, for example, or you might have, even graphs that don't have an embedding. And traditionally, we have, as kind of the geometric data analysis community, we have had many sub-communities that each deal with a particular kind of representation and develop their own tools. And a lot of my goals are basically to develop tools that are applicable across different data representations. And the second goal, which is kind of related, is to exploit detailed relations in the data. So I'll describe what I mean in just a second. And so for today, I wanted to focus on one particular problem, which has been at the heart of a lot of my research, which is shape correspondence. And it's really just summarized in a single image like this. So the problem is given a pair of shapes that are maybe non-rigid, so they have some arbitrary deformation, to find correspondences or relations between them. And the functional perspective that I would like to emphasize in my presentation is that essentially, rather than comparing points on objects, so finding correspondences between points, it is often easier to compare real valued functions. So here I'm showing two shapes where a function is represented as a color. So basically every point has a particular color. And it is often beneficial to find relations not between points, but between functions, because it makes a lot of the computations easier. And the main idea is that these relations between functions can be represented as matrices. And this is what I call this functional perspective. So my plan for today, for today's talk, is to kind of go in 3 parts. So first, I wanted to discuss some of the influences and foundations behind a lot of this work. And then I'll talk about the functional map representation and functional representations for other concepts like vector fields and deformations. And then in the last part, I'll talk about the most recent extensions dating from the past year that have to do with learning. And so when thinking about this talk, I was thinking what would be a good structure and what would be maybe something that maybe not so specific to a particular problem that I'm working on. And I wanted to give, for the first time, and this is a bit of an experiment for me, so I hope it works. I wanted to give a kind of a history of how some of these ideas have come about. And I hope that some of this history will be also useful for maybe if there are PhD students in the audience, to a little bit understand sort of the genesis of ideas, because I really want to emphasize that ideas don't come about in isolation, and they come from, you know, previous works. So I wanted to describe some of these works that really have influenced me a lot. So as I mentioned, I will present not only my works, but actually also works of others. So when I started my PhD, I was kind of given this problem. And my problem was basically isometric shape correspondence. So the task is, I give you a pair of shapes. So here they're denoted as M and N. And the goal is to find a mapping T, so basically an association between points on M and N that approximately preserves geodesic distances. So what's a geodesic distance? It's the length of the shortest path that remains entirely on the surface. And the idea is that if I can do this, if I can solve this isometric shape matching problem, then I can find correspondences between non-rigid shapes, like, for example, humans in different poses. And so the simplest way of writing this problem is to say, basically, let's look for a mapping T that approximately such that the geodesic distance between every pair of points X and Y is the same as the geodesic distance between the corresponding points T of X and T of Y. And the challenge with this problem is that immediately you can see that the space of solutions is highly nonlinear and non-convex, because it's basically we're optimizing over all possible correspondences. And this is very, very difficult. So, you know, I was basically given this problem in the beginning of my PhD, and I was like, okay, this is very difficult, so what do I do? So I want to kind of walk you through some of these inspirations. So actually, kind of going back to really my roots, I realized that the first truly inspirational paper for me was a paper that was published at SMI in 2006. And it was a paper by Bruno Levy. And it has a very catchy title. It's a beautiful title. It's also a beautiful paper. It's called Laplace-beltrami Eigenfunctions Towards an Algorithm That Understands, quote, Geometry. And I was really, really intrigued, because I felt like I was, you know, starting my PhD, and I felt like I didn't understand geometry. So if there's an algorithm that understands geometry, that's fantastic. So basically, this paper kind of advocated the use of what are called Laplace-beltrami eigenfunctions in geometry processing. And so, you know, basically, this is taken from the abstract. When applied to a sphere, this function base corresponds to classical spherical harmonics. On more general objects, it defines a function base as well adapted to the geometry and the topology of the object. So what does this mean? So I guess, you know, most of us are familiar with the classical Fourier basis. So if you look at the periodic domain, so it's this space between 0 and 1 on the real line, and consider functions on the space, then a classical result from the 19th century is that any sufficiently nice, so there are some technical conditions, function can be written as a linear combination of Fourier basis functions, right? So these are sines and cosines. So for example, if I have this kind of step function, I can write it as a linear combination of the Fourier basis. And the coefficients in this linear combination are simply given as the inner product. So it's the integral of the original function I'm trying to approximate and the basis functions. These are the cosine, sines and cosines in the Fourier case. And what we can also do is that we can represent this function using a truncated basis. So if you take the number of basis functions you use to infinity, then you can represent any function or any kind of regular function to arbitrary precision, but you can also stop. So you say, okay, I'm only going to use 5 basis functions, and then you're making some error, but already you're making a good approximation. And so in Bruno's paper, in this SMI 2006 paper, he basically advocated the use of the Laplace-beltrami eigenfunctions. And what are those? So these are the eigenfunctions of the Laplacian matrix. So the Laplacian is like a cotangent Laplacian, for example, which is used before, especially for shape parameterization. And these are basically generalization of Fourier bases to graphs and surfaces. And they have many of the similar properties as Fourier bases. So for example, they're ordered by frequency in the same way as the Fourier basis is. So the frequencies are exactly the eigenvalues. So here's an example of the Fourier basis. So the Laplace-beltrami eigenfunctions on some shape. And they can also be used to express functions as linear combinations of these basis functions. So if I take a function f, I can represent it as a linear combination of these Laplace-beltrami eigenfunctions. So for example, in this paper, he presented this idea and said, okay, we can represent different signals. So for example, the 3D coordinates can be thought of as a signal. So, X, Y, and Z can be thought of as real valued functions. And we can try to reconstruct them using a progressively larger number of basis functions. And this is the kind of results that you get. You can also do this with normal vectors, for example, for appearance, right? So these are all results from that paper. So this is really inspiring to me because I thought, okay, so these basis functions, somehow they encode geometry, but there's a problem. And the problem is that basically the Laplacian eigenfunctions, they depend on the shape. And this is good and bad. So it's good because they encode some of the geometry, but it's also bad because if you want to compare shapes, you cannot compare eigenfunctions directly. So here I plot, Laplace-beltrami eigenfunctions on two different shapes. And you can see that there are actually two issues. The first issue is that the basis functions are only defined up to sign, because if a function phi satisfies the eigenvalue problem, minus phi also satisfies the eigenvalue problem. So this is the first issue. So you see, for example, here the two functions differ by sign. And the second problem, which in some sense is even more fundamental, that basically very quickly these functions can look quite different. So basically, for example, here, this 9 eigenfunction, they already look very, very different. So you cannot compare them. So, that doesn't solve our problem. Now, the second paper that I was really influenced by is a paper from SGP 2007. It's a paper by Ray Frstamov. And basically, in this paper, he proposed what is called a GPS embedding. And in the abstract, I was really, really taken by this one sentence, which he said, the GPS embedding captures enough information to handle various shape processing tasks, such as shape classification, segmentation, and correspondence. So this is the problem I was working on. So, okay, great. We can use these ideas and can try to solve this problem. And so in this paper, he proposes basically a kind of a signature for every point. So given a point on the surface M, we associate with this point a vector of basically the values of the eigenfunctions at that point, right? So the first value is the value of the first eigenfunction at P, second eigenfunction at P, etc. And they're scaled by the square root of the eigenvalues. There's a specific reason, which for me is not important right now. But essentially, this is nice because these eigenfunctions are invariant to isometric deformation. So, you would hope that somehow this creates a signature and that allows you to find correspondences between points. The problem is, as I mentioned, each eigenfunction is only defined up to sign. So actually, if I take two shapes and on one shape, it might be, minus the sign. So I cannot compare these signatures directly. And so we thought, okay, so this doesn't help us solve our problem yet. So what can we do? And another thing that in general, I try to do, and I find it extremely useful, is to read, math books and papers, because they often have insights that are kind of timeless. So there's a very beautiful paper from 2005 by basically researcher Alexander Grigoryan, and he talks about different properties of heat kernels and weighted manifolds and applications. And in basically using the heat kernel, this is a work that we did in 2009, we said, okay, let's take, instead of looking at the eigenfunctions directly, let's look at a weighted combination of eigenfunctions, of squares of eigenfunctions. So you see the sign disappeared. And also we take this weighted combination. So instead of thinking as a vector of values, we basically sample in time parameter. And so this led to this heat kernel signature, which is a kind of a signature that allows you to compare points on different surfaces. The advantage of this signature is that it's canonical. So basically this allows you to compare points on different surfaces. And so, okay, this is great. This is what we're trying to find. We're trying to find correspondences in different shapes. But the problem is if you find correspondences between different points, there's no consistency. So each point is mapped independently. So here I'm plotting basically the similarity of points on different shapes. So here are superimposed like many poses of the same horse, and the points in blue correspond to similar points in the descriptive space. And you see that, for example, to this point, there are many similar points. And if you take the most similar point, maybe it's going to be this one. And then for a nearby point, it's going to be something totally different. So there's no consistency when you do mapping just based on descriptors, right? So we need some global map consistency encoded. So that doesn't, solve our problem completely. And then I was also reading a book completely by accident on functional analysis. And basically, this is like a pure math book, but it's one of the most beautiful math books that I've seen. And if you're interested in functional analysis, I'd highly recommend it. And so, first of all, it's a math book, so I had trouble finding a good quote from it. But you know, this is like kind of very dense material. So say the material included in the first volume is clear from the table of content. You know, it is like mathematicians; they don't joke around. So, like kind of more importantly for me, it was a big realization that, you know, the space of functions has a very, very rich structure. And for example, when they talk about metric spaces, the examples they gave were basically a metric space built on top of the space of functions. And I was, you know, really kind of inspired by this, and I thought this is such a beautiful property of functional spaces. So can we use this for this problem? So, you know, like I've been thinking about the same problem, and at that point it was basically the end of my PhD, and I feel like I kind of actually didn't solve the problem that I started with, and I was kind of really disappointed. But this work really just led to a simple question, and the question was the following. So suppose that I give you two surfaces, right? And I have two functions on these surfaces. Let's say that I express each function in the corresponding basis. So I have some function f on m, and I express it as a linear combination of the basis functions on m. And I have some function g, which I express as a linear combination of the basis functions on n, right? And the question is very simple. What is the relation between the vectors of coefficients? So if I consider, you know, this set of coefficients, it's a discrete set, so I can think of it as a vector. What is the relation between the sets of coefficients a and b, right? And actually, it turns out that the relation is very simple, and the answer is that there must exist a matrix such that for any pair of corresponding functions, basically the set of coefficients b equals to c times a. Okay, so c doesn't depend on a or b; it's some universal transporter. And in this case, corresponding functions means that they arise from some fixed point-to-point correspondence. Right. So if there is some correspondence, there must exist a C such that for any pair of functions, C times A equals to B. If I just state it like this, it might not be obvious why that is the case. So I think the simplest way of seeing this is actually to explicitly construct what the C is, right? So I'll do this in the next three slides. And this is basically the idea that we proposed in SIGGRAPH 2012. And this kind of is the foundation for a lot of the things that I'll describe later. So the idea is that, okay, let's suppose that I have this pair of shapes M and N, and I have a mapping T between them. So this is some correspondence between points on N and points on M. Let me write, so once again, I'm presenting this material in a slightly different way, but I think this is actually more clear. So let me write this mapping as a matrix, right? And this binary matrix is basically will have the number of rows equal to the number of vertices on N, and the number of columns equal to the number of vertices on M. And I'm going to say that this is a binary, so 0, 1 matrix, and pi ij is equal to 1 if and only if t of I equal to j. So basically, I'm just taking this this correspondence and writing it as a matrix, as a binary matrix. So it's kind of trivial. Now, there's a nice observation, which is the following. So if I have a function f, I can write it as just a vector of values, right, on M. And I can find a corresponding function on N, okay? And the corresponding function on N is just that for every point y on N, I just basically borrow the value of f. So I have f, so g of y equals to f of t of y, right? So remember, we have this t that takes points from here to here. So for any point here, I just look where it comes from, where it gets associated, and then I just take the value of f. And in matrix notation, you can write it like this. So g is equal to pi times f, right? That's it. There's really nothing else, right? So remember, g has the number of elements equal to the number of vertices on N. Now, this was in the indicator basis. Now, if different functions are expressed in a different basis, you can write the same idea, but in basically by just appending the basis. So suppose that I have some function expressed in a particular basis. I first, decompose it into the full. Basically, I use the matrix of basis functions to construct the full function. Then I transport it using the SPI, and then I project back onto the basis on the target shape. So this is basically the whole construction, and this matrix C that you can write in a particular basis is what we call a functional map, right? And what is nice is that, you know, when we're dealing with dense, complicated meshes like, you know, human shapes or these armadillos, they can have thousands and thousands of vertices, or maybe even millions. But when you have a multi-scale basis like the Laplace-beltrami eigenbasis, you can take any map, any correspondence, and express it as a matrix in a fixed basis size. So for example, if I use 30 basis functions, and this basically means that the correspondence becomes a small matrix, and the small 30 by 30 matrix can capture very precise maps. This is an observation that we made. So now we kind of transported this problem between finding what this pi is to finding what the C is. Right? And what's kind of nice is that many properties of maps actually become easier to express using this functional map representation. So for example, I just give a couple of examples. So a correspondence is isometric, so it preserves geodesic distances if and only if this matrix C commutes with the Laplacian, right? So this is actually relatively straightforward to show. I won't give a proof, but essentially because the Laplacian fully encodes geodesic distances. Another property is that the mapping is locally volume preserving, so it preserves, you know, basically local volume elements if and only if the functional map is orthonormal. So this is actually a weaker condition. And finally, the mapping is conformal if and only if there's a relation between basically the Laplacian and this functional map. So all of this to say that different geometric properties of correspondences become algebraic properties of functional maps. So kind of what it means is that, you know, when you're dealing with geometry processing, we usually have a lot of trouble expressing geometric concepts in kind of ways that we can optimize on a computer. And here, a lot of these properties become very simple, like algebraic properties on these matrices. So based on this representation, we proposed a kind of a pipeline for computing correspondences. So if I give you a pair of shapes, how do you actually find a correspondence? So this pipeline works like this. So basically I compute some basis functions. So for example, the Laplace-beltrami eigenfunctions, and I store them as matrices, as columns of matrices phi m and phi n. So typically these are like approximately 80, 30 to 80, depending on the application. Like usually not more than 100. Then we also compute some descriptor functions like Gauss curvature or this heat kernel signature on the two shapes. We express them in a particular basis as columns of A and B. And finally, we basically solve for the optimal functional map by saying, okay, find a matrix C such that basically it aligns the descriptors, so C times A equals to B, and also it commutes with the Laplacian. So this is this prior that says we are looking for near isometric correspondences. And what's nice here is that, for example, when I'm even to check whether a correspondence is near isometric, you would presumably need to compute all pairs of geodesic distances, which is expensive. But here we kind of avoid that by basically looking at just the Laplacian. And finally, once you have the C, you can convert it to a point-to-point map, right? So this is a very, very simple pipeline that we proposed, like I said, in 2012. And at the time, it kind of gave state-of-the-art results on these different relatively easy benchmarks by today's standards. And so, I would say that basically gave kind of reasonable results. So given these different shapes, you can find relatively good dense correspondences between them. And of course, once you have correspondences, you can do many things with them, like you can do texture transfer or deformation transfer. Like, for example, we saw in Mario Bocci's talk yesterday, you can do even template alignment, and then once you have a good template, you can create avatars like they do in a beautiful way. So this kind of is a very powerful tool. We also evaluated numerically against some existing techniques at the time, and basically you can often see these kinds of plots where on the x-axis you see some error, and on the y-axis you say what is the percentage of correspondences, the points that I computed that are below this error. And so, for example, on a mesh like this, a radius of 0.05 is approximately of this size, and at the time we got something like between 80 and 90% of all the points are within this radius of the ground truth. So it's not amazing by any means, but it's reasonable, and often it's good enough to get you started to do some non-rigid alignment. And of course, this is a relatively old result now, and so we can do much better. So this was kind of the beginning of my story in some sense. And once we realized this, there are many questions that naturally came about. So the first question is, can we represent other concepts as linear operators, right? So here we show that correspondence can be, or mapping can be represented as a linear operator, matrix. And maybe there are other things in geometry we can do in a similar way. The second question is, can we synthesize shapes from functional maps? So can we, given a source shape and a functional map, can you create a target shape? And then there are many questions about whether we can improve this basic pipeline, for example, by improving descriptors and doing some learning. So these were, to me, and still are, very exciting questions, and kind of have filled my work life for the past 8 years or so. And so today I'll give an overview of some of these results. So basically in terms of extensions to other concepts, so can we view other geometric concepts as operators? Basically, there are two directions that we have taken that turn out to be very fruitful. The first one is representing vector fields, and the second one is representing basically shape distortion, or comparing shapes and doing shape synthesis. So I'll briefly give an overview of these two directions. So the first one has to do with vector field analysis and vector field design. And on the surface, it doesn't seem like it's actually closely related to shape correspondence. And why would vector fields be represented as linear operators? But it turns out this is actually a common point of view in mathematics. So a vector field, what is a vector field? So if I give you a surface, you can think of a vector field in two different ways. One is, you can think of it as a kind of a direction, like a vector per for every point in the tangent space. And the second point of view is you can think of a vector field as a flow. So basically, if you just take a particle and start moving in the direction prescribed by a vector field, that gives you a flow. And so a vector field is also kind of a prescription for motion in some sense. And there are many, many different representations of vector fields. So I just give a brief, mention of some of the works, and they each have their own advantages and disadvantages. And again, I would say that similarly to the correspondence work, a lot of the representations are kind of very local. So you can do some local analysis, and it's not always, in some cases you can, but it's not always easy to get global properties of vector fields. So there's a different representation that we propose, and I should say that a lot of this work is done in collaboration with Mirella Ben-Hen and Omri Azenkot. And so we basically try to create a different representation for a vector field. So the idea is actually very simple. So suppose I have a vector field. The idea is that we can associate to this vector field a linear operator, which we denote by dv. And it's a linear operator that acts on functions. So given a function f, so any real valued function, I can take the gradient of f, and then I can take the inner product. So in this case, the inner product is at every point. I just take the inner product between the corresponding vector vx and the gradient of f at x. So this gives me a scalar function. And so basically this is an operator that takes a function and produces another function, right? And what is remarkable is that this operator uniquely encodes v. So if I know how it acts in different functions, I can recover the vector field, right? And this turns out, again, I learned this along the way, that this is a very common idea in differential geometry, and this is called derivation. So derivation is just an equivalent way of expressing vector fields. And so we basically kind of were very excited about this idea, and we tried to discretize it in practice. So it's relatively simple how to construct this dv operator in a triangle mesh. And also you can show that the same uniqueness statement also follows in a discrete setting. And once again, because we have a linear operator that acts on functions, we can represent it as a matrix. So basically, once again, a vector field becomes a matrix, right? So similarly as the correspondence or mapping was a matrix, now vector fields become matrices. And so, this is one vector field in the corresponding matrix. This is another vector field in the corresponding matrix. And so, we just took something and we wrote it in a different way. So what we try to argue is that this matrix or this operator representation of vector fields has nice properties. So for example, there's something called a killing vector field. So a killing vector field is a vector field that if you flow along the basically along this vector field, then the flow lines preserve the geodesic distances. So it's a kind of an isometric version of vector field. So for example, on a torus, if I have a vector field that flows along the torus, then it preserves geodesic distances. Or on this vase, it's the same. Now, it's kind of not straightforward to say how do you compute such vector fields that preserve geodesic distances. But in this operator representation, you can show that this is equivalent to just asking that this dv operator again commutes with the Laplacian. And to compute so this actually makes it extremely easy to compute near approximately killing vector fields. So we propose basically a method that's in the kind of at its heart just takes a least square system. And it produced, very kind of realistic, approximately killing vector fields. Another point which is useful in this operator representation is the following. So suppose that I have some vector field V and I have some function on the surface. Then you can write what is called the advection equation. So the advection equation is basically saying, how does this V, how does this function change if I kind of move along this vector field? Right, so if I set up a partial differential equation that says that the evolution in f of f in t should be the same as just advecting, along the vector field, and this is actually equivalent to saying that basically the evolution of f in t is governed by this dv, this derivation operator, right? And so this is very nice because it actually can be summarized as follows. So if I have some initial condition f of 0, so this is my function at 0, to find f of t at any time t is equivalent to just finding the exponential of this dv operator applied to f of 0, right? And in a discrete setting, this reduces the advection to just matrix exponentiation, which is very, very easy, or relatively easy to do. So this kind of led us to investigating, so where does the advection equation arise a lot? So many of you would know that advection equation is common, for example, in fluid simulation. So based on this, we proposed a method for doing fluid simulation on surfaces. So this is just one example where we took some basically, so typically fluid simulation is on Euclidean domain, like in 2D or in 3D, but you might also try to simulate fluids on surfaces. So here is an approach that we had based on this relation between the advection equation and the derivation that is very stable. Okay, the same idea and the same relation between vector fields and these derivations also can allow us to find either symmetric vector fields or vector fields that are related on different surfaces. And so we use this idea to find basically either joint quadrangulation, so basically given a pair of triangle meshes and a correspondence, a very rough functional correspondence between them, find a quad mesh that basically is consistent on the two surfaces, or a quad mesh that is symmetric. And this is all based on this sort of algebraic properties between vector fields and mappings. So that's, that was kind of one nice thing of representing vector fields as linear operators. And another direction that we investigated was how to represent shapes as operators and how to do shape synthesis. And this is something that I'm still working on, and I'll mention some very recent results in this direction. So one of the motivations for this work is that if I give you a pair of shapes, so for example, here I have these bones, and I got this bone data set from researchers in the Natural History Museum in Paris. And they're interested in basically finding regions where the two shapes are similar and regions where they're dissimilar in some sense. And this allows you to basically say, like, for example, anatomically, what are the two different animals, whether they have some differences in specific locations. And this is helpful because then you can try to link that to their behavioral patterns, etc. And so finding these detailed relations, so regions where things, where the two shapes are similar or different, is kind of not straightforward, because a lot of the previous metrics for comparing shapes are very global, so that they essentially assign single number to this shape similar at a certain, with like 2 to this other shape, and that's usually not sufficiently detailed. So this led us to a idea which we call shape difference operator. And before defining it formally, I wanted to give some intuition. So the first point is that when I have a pair of shapes like these two, a functional map, so basically a correspondence, only allows you to transfer function values. So it doesn't tell you anything about how things change, right? So if you think about this, for example, binary correspondence matrix, it doesn't provide any information about any kind of distortion, right? But if you impose some additional structure, so if you say, okay, for every function, I also can measure its norm, so for example, the L2 norm, then the L2 norm, for example, of the indicator function is just the area of that particular of that region. So if I have an indicator function of a region, so if f is an indicator, then the squared L2 norm is just the area of that region. And so what you can do is then you can say, okay, can I compare the L2 norm before and after transfer, right? And this already gives you some notion of, okay, things maybe there's some distortion because maybe some region shrunk and some region expanded. Okay, so that's the motivation. And so what we propose is basically what we call a shape difference operator. And this is just the same idea, except it acts on pairs of functions. So shape difference operator D is a operator that is defined implicitly and is defined as follows. So for every pair of functions f and g, we want basically this D operator to be such that when I apply it, the inner product on M is the same as the inner product on N. So this is kind of just the picture. So say I have a pair of shapes M and N and I have a functional map between them. Then if I look at a region here, then you see that basically if I map this region onto the target shape, something must change, right? Because the area of that region changed. So basically this D is a kind of a corrector. It corrects for the change in the norm. But if I have a different function on a different location, then there shouldn't be any correction because there's no change. So the D basically acts as a kind of a corrector for the norm. And so this property, this D operator basically encodes a lot of the distortion induced by a map, right? And you can show that it exists and it's unique. And so depending on what you choose for the inner products on surfaces, there are two natural inner products. There's L2, where you basically take the integral of the two functions, and there is the H1, where you take the integral of the gradients of the two functions. And so depending on which inner product you choose, you get a different shape difference operator. So we call basically these area-based and conformal because they're preserved by either area-based or conformal maps. And in the discrete setting, there are very, very simple expressions for both of these, okay? And so what's nice is that basically if I have a collection of shapes, I can then represent every shape in the collection by some shape difference operator from some source shape. And so, for example, if I have this sequence of running courses, what I can do is I can basically take some fixed shape like this one and then compare all of the other shapes to that shape. And then I can find an embedding. So this is actually a circle. So there's a loop structure in this in the sequence. And also we can find what are the regions on the surfaces that are responsible for this variability, because we have detailed information about where things change. And so this kind of allows us to highlight the changes. So this is the definition of shape difference operators. And now what basically you can ask is that suppose that I give you a pair of shapes M and N. And so this is related to this question, can we synthesize shapes from functional maps? The question is, if I give you a pair of shapes M and N, and I compute, for example, some shape difference operator from M to N, can I recover N from it, right? Because recovering a shape from a functional map is impossible because it just maps values, but recovering a shape from shape difference operator is at least feasible. I mean, you can ask this question, like, is it possible or not, right? So can we recover N back if we have these difference operators? So this turned out to be not an easy problem, but basically in this paper in 2017, we showed that the two shape difference operators, the area and the conformal one, they fully encode the discrete metric, so the edge lengths of a triangle mesh, and those can be recovered by basically solving two linear systems that are almost always full rank. So this was a kind of a theoretical result. And we try to implement it in practice. And if you have perfect information, it's possible you can recover the edge lengths. And so here's, for example, we have a source and target, and then we try to recover the target using this intrinsic metric. And so this allows, if you're lucky, then basically, and you do a lot of regularization, you can recover the shape, or at least you can recover the edge lengths, and then this gives you the intrinsic metric of the surface, and then recovering the full shape is very challenging. So I would say, so this was kind of a lot of, my take-home message from this project was that any paper that claims to recover the shape just from the intrinsic metric is doing something, there's some very strong regularization. And it's not easy in general, because there are many shapes that have the same or very similar edge lengths, but don't have the same pose. So recovering the pose is a difficult problem. So in this 2017 paper, we showed a different way of recovering the pose, but it was kind of very computationally heavy and not very practical. Now, more recently, we asked the same question, but from the point of view of learning. And this kind of brings me to the last part of my talk. And essentially, what I'd like to argue is that a lot of these constructions are very naturally, they fit with the learning pipelines. So the problem is still the same. So suppose that I have some shape, and I can reconstruct it using a shape difference from some base shape. And so the shape difference is a matrix, right? So I have these two matrices. So in basically, the shape becomes a pair of matrices. And the shape recovery or shape synthesis problem becomes, given two matrices, can I recover the embedding? And what is kind of nice is that, matrix is something that very, advanced computer vision based learning pipelines are good at dealing with, because, they're basically images, right? So you can use, for example, convolutional neural networks. So in this paper in 2019, we basically asked the same questions, that can we train a network that, given a set of shape difference operators, uses maybe convolutional neural networks to recover the shape itself, right? And so, this is what we did. And so basically, what you can do, because you have these very powerful tools and you have strong data regularization, you can do this. So you can actually recover the shape relatively accurately. Now, one question is like, why would you want to do this, right? Because you could train end to end, right? So you can do, for example, like what is commonly done in a shape autoencoder. You just give the shape, you pass it through some layers, and you, for example, like a point net is a famous architecture. You have some intermediate latent representation. You can synthesize the shape back. Now, one problem with this idea that I found, and I think it's a little bit hidden in some sense, is that like, once you can train this, certainly, but then the structure of the latent space is not completely clear. So for example, one application you can do if you train, for example, PointNet++, and do interpolation by doing interpolation in the latent space, the kinds of results you can often observe is that something like this, where basically you have a lot of intermediate distortion, right? And fundamentally, I think this is related to the fact that linear interpolation in the latent space has no geometric meaning. I mean, if it works, you're kind of, that's good, but there's no reason for it to work. At least I don't have, like, I haven't been able to find a good justification why linear interpolation in the latent space really makes sense geometrically. So instead, what you can do, like for example, with this operator net approach, because we have a well-defined algebra on these shape difference operators, we can synthesize intermediate shape difference operators, and then this allows us to do shape interpolation very accurately without doing this kind of distortion. Also, we can do shape analogies. So shape analogies is, given a shape A and a shape B and another shape C, find a new shape like X, such that the difference between C and X is the same as the difference between A and B. And once again, in the learning community, this is typically done through additive algebra in the latent space. But again, I don't think there's a very strong reason why geometrically that makes sense. So you can often get lots of distortion. So for example, in this case, we can synthesize a shape that looks basically is like a female version of this male shape. And actually it's quite subtle, because not only, the pose is preserved, and it changes the shape structure. Actually, it's not just that, you know, there's some basic features that are added or removed, but the shape structure actually changes. So there's some, I think this really has to do, I think, with the fact that this algebra is well defined on the difference operators. Okay, and so this is for shape synthesis. And in the last couple of minutes, I wanted to show some very recent results, and they have to do with this shape correspondence problem. So going back to shape matching. So the pipeline, so I think there may be some questions. So I'm actually not completely sure. There's some comments. If you don't mind, maybe I can keep the comments until the end, and then we can go back, if that's okay. So because I'm not entirely sure if this breaks the presentation.
Was that,
yeah?
That you have 2 minutes left.
Ah, okay, perfect. Okay, thank you. Okay, so I'll be very quick in this last part. So basically, you know, we have this pipeline for shape matching, and one problem in this pipeline is how do you find good descriptors, right? And so so what are some good features, good descriptors? And if you have bad descriptors, bad features, then you can have bad correspondences. And this is a real problem with this functional map based pipeline. Now, there was a paper that was proposed in 2017 called Deep Functional Maps, where the idea was, it wasn't from us, it was from Litani et al. The idea was, let's learn the features, right? And we have some ground truth correspondences, and let's learn the features such that the resulting maps are as close as possible to the ground truth. And what they did is they said, let's start with some input descriptors. So they use some short descriptors and then try to modify them. And we proposed last year to basically extend this idea, but in an unsupervised way. And so how does this work? The idea is that let's learn features, but instead of comparing our functional maps to some ground truth, let's just say, okay, how good are these functional maps? And once again, this is using this idea that we can impose some global structural properties. Like, for example, the resulting map should be bijective, or should be area preserving, or should be near isometric. And basically what we show is that all of these losses are differentiable with respect to C, and you can basically backpropagate to the weights of the descriptors. And so, you know, if you do this learning, you obtain some very high quality features, even though you don't have supervision. Right? And finally, and so basically this kind of obtains state-of-the-art result among unsupervised methods. So maybe let me skip these results. And finally, let me just mention a very recent result that's not published yet, but it's appearing in CVPR, where we basically show that you can actually learn descriptors not only by modifying some given descriptors, but actually learning from the raw data, from the geometry itself. So this is a different architecture that we proposed. And what we show is that you can actually add a regularization inside the network. So this is slightly non-trivial result. Maybe I won't go into detail exactly. And so this basically produces very high quality, fully automatic descriptors and, you know, high quality correspondences. And what is nice is that we compared to basically existing methods, which are just based on the geometry, and they don't have this functional map representation. And what we show is that essentially by using this functional map representation inside the network allows you to avoid overfitting and construct high quality maps, even with a relatively small number of shapes in the training set. Okay, so that's basically all I wanted to say. And my main message in this talk was essentially that many concepts in geometry processing can be represented as linear operators. And there's a kind of a nice relation between these operators, and they can kind of communicate in a very natural way. And what is also nice that I've been discovering in the past couple of years is that this linear algebraic structure, which first was convenient just for optimization, actually turns out to be very convenient for learning as well. So we can use some of these powerful tools for learning to get good correspondences. So I will post my presentation. So I added some links to some of the references that I mentioned. And yeah, thank you very much.
So thank you very much for this very inspiring talk, Max. So let me check if there is any question from the audience. Yet, but if you want to ask questions, please write them in the chat or use the raise hand button. If you can't find the button, please look at the bottom of your Zoom window and click on the participant button, and then you will find the raise hand button at the bottom of the new participant frame. So, check. Okay, so there's one question from Oleg. Okay, he asks you, do you use any other representations than point
clouds and polygon mesh? Yeah, it's a great question, and so I have in some projects. So for example, graphs is something that I'm very interested in, and I didn't present in this talk, but you can of course construct very similar concepts on graphs, like the Laplacian has very natural discretization. One thing that I've discovered with graphs is that often the data is not so easy to find.